Hi, I'm Andy and welcome to my walkthrough of the 2020 Sans holiday hack. In the previous video we fixed the damage that Jack Frost did to Santa's sleigh. The next objective is to find the vulnerability that he coded into the tag generator. As always, we'll stop off to see one of Santa's elves to help them with the terminal challenge in return for some hints, but not before jumping back through the painting to return to our normal form. Down in the kitchen, Holly has a terminal running the Redis database and a web server. They're concerned that there's a remote code execution vulnerability and want us to use it to print the source code of index.php. The only accessible route is via maintenance.php. Running curl to fetch that location returns a message saying that we must specify a value for the command property. It suggests a value of help, so let's try that. It looks like this maintenance.php script is taking the value specified by command and passing it as an argument to the Redis command line interface. At least it's smart enough to redact the password to the Redis database in its output. The info command provides a few more details about the server, including the version of Redis, location of config file, and server OS. Redis is an in-memory database, meaning it typically doesn't store any data to disk. But it does have a feature to do this, and with access via the administrative command line interface, we can pick the file name and folder to save to. If the Redis server process is able to write files to the web server's root folder, then it could be possible to inject our own PHP code to then get executed by the web server. To do so takes multiple steps. First, update the Redis config to set the save directory to the typical web root folder under var www html. Next, set the file name of the file to save as. Then, clear the database of any records using flush all. And insert a single new record named test with the contents being a little snippet of PHP code. Note the need to escape certain characters and use plus symbols in place of spaces. Then, commit this database to disk with the save command. And now, curl that new file. Curl returns a warning about the data containing binary data, but we can dump it out to the terminal anyway with the --output option. There's a lot of junk here as this is a Redis database format, but the PHP payload is visible in the middle. However, it's odd that this code is visible. This should have been executed by the PHP interpreter. Turns out that I fat-fingered the payload and missed the question mark in the opening PHP tag. After updating this, resaving the database, and trying again, that snippet of PHP is properly interpreted. With that test now working, we can upgrade the payload with a shell exec command to run a binary. Here I'm just specifying the id command, again as a test to make sure that this part is working before moving on. This successfully prints the output of the id command, showing the user and group IDs of the account that the command is being executed under. Finally, we just need to modify the command to instead run cat to print the contents of the index.php file. With the contents now printed, we are rewarded with the completion achievement, and Holly shares some clues for the main objective. We are tasked with investigating the tag generator, specifically finding the value of environment variable greets, which sounds like it's been left as a calling card by Jack Frost when he corrupted the app. We're again denied access to the tag generator in our normal form, so must jump back through the painting to enter Santa mode. Once in the app, a good starting point is to play around and become familiar with its purpose and features. It allows the user to create a design for a gift tag, either starting from a blank or a pre-made template. Text and images can be added, and there's a button to download the final design. A button exists to upload new images, although an error is generated if a non-image file is uploaded. This error message exposes several key points. Firstly, uploads are placed, at least temporarily, into the /tmp folder. Second, the server-side code is written in the Ruby programming language. And third, the server-side code either partially or mainly resides in the file app.lib.app.rb. Let's dig deeper into that file upload with browser dev tools. A new image upload shows a post request containing the image data, which returns a GUID-based file name in the response. This is followed by a GET request containing this same file name, where the response is the image that's just been uploaded. So, the value returned by the first request is used as an input into the second request. But we can specify our own value for this second request. Let's give it a try with a value that probably doesn't exist. This returns a 404 error, file not found. Makes sense so far. But is this code restricted to just a file name, or is it possible to specify a folder name too? Still a 404. That's good, it didn't complain about the presence of the slash. Now, is it possible to move upward in the folder structure too? Say, to extract a copy of this machine's password file. The exact number of double dots isn't too important here, we just need enough to reach the file system root, and any extras don't have a negative effect. This returns a 200 response code, suggesting success, but the response itself is a broken image. It looks like the browser is trying to be clever, and based on the content type in the response header, is attempting to render the response as an image. We can bypass this using curl. And there we go, the password file for the machine. That's confirmation that this part of the web app is vulnerable to a local file inclusion vulnerability. This can be abused to access any file which the web server user can access, including the source code of the app, which the earlier error message advised was in app.lib.app.rb. Great, we can fetch that too. Although it's pretty big, so let's redirect it to a new file, and open it in a text editor for easier reading. A browse of the code reveals more about the operation of the upload functionality, including on lines 92 to 100, showing that the supported file types are PNG, JPEG and ZIP. On line 33, there's specific code to extract contents from a zip file and process each file individually. Code concerned with validating file names has been commented out by Jack Frost. And on line 78, there's a system call to resize images. This could be injectable, especially as validation is now missing. Let's dig deeper into that file upload section a bit more, and try to inject some content into the file name to trigger remote code execution as part of that call to the convert app. After all, the goal here is to grab the value of an environment variable, which can be achieved if we're able to run the env command. Note though that this conversion process happens in a separate thread, and so we'll probably have to direct the command output to another file and fetch that as a separate follow-up request. The system command being run is this, and the #filename part gets replaced with the name of the file being uploaded. We can simulate a file upload in curl as follows. The -f option instructs curl to upload the contents from a local file, in this case just a test image. This looks to be working, but we want to be able to manipulate the file name. This could be done by changing the name of the file on disk, but we'll probably need to use a few special characters as part of our attack, so it's easier to specify the file name property to override the name which the web app sees. This can be further verified by making the PNG file appear to be a text file, and as expected, this produces an error. However, this error exposes a flaw in the plan. During the upload process, the file name is being rewritten. Only the file extension remains intact. This is clearly to avoid a clash if multiple people attempt to upload files of the same name at the same time. A closer look at the source code reveals an alternative route to achieve the same. This code is used to handle zip files. Each file is extracted and then processed like any other file. And so, whilst the file name of the zip file will be modified in the same way as we saw before, it appears that the contents of the zip file do not have their names modified. Okay, so we possibly have a way of manipulating the file name. Now let's take a step back to work out what we need to set it to in order to achieve our desired exploit. This is the command line which is being run to perform the image resize, and these are the parts which are replaced with the name of the input file and output file. Note that both are enclosed in single quotes, so that'll need taken into account to ensure any other special symbols are treated as operators. Ultimately, we want to run the env command, and send its output to a file which can be read later. And we saw in previous videos that multiple commands can be chained together separated by a colon. To achieve this within the constraints of only being able to manipulate the file name, we need to specify an input and optional output file name ourselves, and then add in the semicolon and our desired command. We've already seen that this app will reject anything which doesn't end in a .png, .jpg, or .zip, so we need a way of adding that onto the file name without causing an error. One way is to add the hash symbol. Everything after it will be treated as a comment. This has the added benefit of also ignoring the output file name portion of the original command. Now, to create a dummy file with this name, and zip it up, and push it over to the server as an upload. If successful, there should now be a file called rot169.txt which contains the output of the env command. This can be fetched with curl, and there's the environment variable greets with the value Jack Frost was here. We can use the same method to execute any command on the server. A payload such as this creates a reverse shell connection. It's also worth pointing out that the main objective can also be completed in a single request, given a bit of knowledge about the Linux proc file system. This is a pseudo file system, or in other words, none of the items here are actually files. Instead, proc provides a route to access information about running processes. Note that a directory listing shows many numerical folders. Each of these folders represents a running process on the system. Within each are some pseudo files which retrieve information about the process, including environ, which prints the environment variables that the process was launched under. So, if we know the process ID of the web server, we can simply print this via the local file inclusion vulnerability. Thankfully, proc offers an even better option. One of the folders, self, represents the details associated with the current process, and the local file inclusion exists in the context of the web app. So, we can retrieve the environ file from this folder, providing sight of the greets environment variable again. That's all for this video, but leave a comment if you have any questions, or if you used a different method for solving any of these puzzles. We'll pick up the story in part 9, where we'll be using Scapy to inject some handcrafted network packets to seize back control of a machine that Jack's taken over. Feel free to take a slight detour on your way and check out some of my other cybersecurity videos, otherwise I'll see you there.